This video is all about the concept of vectors. A vector is a quantity that has a size and a direction. For example, all forces. Gravity. The gravitational force that we feel on planet Earth has a certain size to it, and it has a direction, as in downwards towards the centre of the planet. Or if we're talking about the gravitational force that planet Earth feels, it has a size, and it also has a direction towards the sun, keeping us in orbit around the sun. If we're talking about the magnetic force, it has a size, depending on how big the magnet is, and it will also have a direction, either towards the magnet or away from the magnet. If we're talking about the tension in a string, or in a piece of rope, or in a spring, again, it's got a size, but it also has a direction to it. Another example is velocity, how fast something is moving and in what direction it is moving in. And acceleration, that also has a size. We accelerate in a certain direction as well. So those are all examples of vectors. Some non-examples: temperature. Temperature has a size, but it doesn't have a direction. It wouldn't make any sense to say that the temperature is 20 degrees north. That wouldn't make any sense. Similarly, mass. If I said that this bag of potatoes weighs 2 kilograms in the direction of southwest, that again makes no sense whatsoever. And volume, that's the amount of space inside an object. It doesn't have a direction. So these non-examples are called scalars. They have a size, but they do not have a direction. So that's the concept of a vector, but the main bit of this video is how can we actually model this mathematically? So we need to look at some notation. Then we can actually do some maths and start to investigate these things in nature with maths. So let's look at some notation. The way we represent a vector is with either a letter that's been underlined or in bold. The reason why it's important to underline it or put it in bold is because if I just wrote A, then that's just how we normally write variables for algebra. So that would just represent a number that I don't know yet. So it would have it would just be a number, it would just have a size, it wouldn't necessarily represent a vector, it wouldn't have a direction to it. So that's why it's important to underline it or put it in bold to show the reader, to show the person who you're communicating your maths to, that it is a vector and not just a scalar. And the way we do it is with these brackets like this. The number on the top here says how much we're going across. The number on the bottom says how much you are going up. So we're talking about having a size in each direction, in the x direction and the y direction. So for example, the vector 3, 4 means to go across 3 squares and up 4 squares. So overall, what I'm doing is this. I'm moving from here to here. That has a size and it has a direction. If I were to do the vector 6, 8, that would be across 6 and up 8. It would actually be in the same direction as the 3, 4, but twice as far. If I were to have the vector, let's say minus 4, minus 4, 5, what would that look like? So minus 4, 5. Well, the fact that the x number there is negative means I'm moving in the negative x direction, 4 squares, and up 5. So that would be like that. If I were to have the vector minus 3, minus 2, that means I move negative 3 in the x direction and negative 2 in the y direction. So I'm moving to the left and down now. So if the number on the top is positive, it means go to the right. If it's negative, go to the left. If the number on the bottom is positive, it means go up. If it's negative, go down. So let's have a look at a few examples. So you can see here that I've written a sentence describing a journey. I've said I'm travelling 8 kilometres on a bearing of 60 degrees. Now, that's a bit awkward in terms of doing maths. I don't want to have to write a sentence like this. I want to be able to have a nice, neat way of writing it, which is what we call this column vector. So I want to know how much am I going across and how much am I going up. So let's say I'm starting at this point here and I'm travelling 8 kilometres on a bearing of 60 degrees. Now remember that bearings are measured clockwise from north. So let me mark my north line in first. A bearing of 60 degrees means this angle will be 60. So I'll be like, that angle there is 60 and the length of this line is 8 kilometres. But I want to be able to represent this as a vector, like I said. So I want to be able to know how much am I actually going across and how much am I actually going up? What are these values? That's what I want to know. Now, the useful thing here is the x and the y are always at right angles. So I've got a little right angle triangle. And I can work out the sides of a right angle triangle by using some trigonometry. So, considering that this angle here is 60, I also know that the angle inside here will be 30. So therefore, to work out the adjacent side here, I can do cos 30 is equal to the adjacent divided by my hypotenuse. And if I now multiply both sides by 8, 8 times cos 30 equals x. And if I type that into my calculator, I get 4 root 3 in its exact form. So straight away I know that I'm going across 4 root 3. So that's the top number in my column vector. Now, to work out the y, that is opposite my angle, so that will be sine 30 equals y divided by 8. And if I multiply both sides by 8, 8 times sine 30 equals y, so I get 4. So my point is, instead of writing this long sentence, I could just represent that mathematically with just this column vector, which is much neater, much nicer to deal with, much more concise. So that's why vectors are actually really useful. And bear in mind, this is just the beginning of this topic. So there is a lot more to be learnt about this. And the more you deal with it, the nicer and easier it becomes to use vectors rather than sentences. Next example. I want to travel 20 kilometres on a bearing of 150 degrees. So let me draw a little diagram. There I'm starting, and if that's my north line, 150 degrees would be, well, that there is to 90, and I need to keep going to get to 150. So that's going to be something like that. Not quite going all the way around to 180, but it's 20 kilometres in this direction, roughly. But like we said before, I want to know how much am I going across, and in this example, how much am I going down? Now, to work out the x and the y here, the angle that I'm missing here would be 60 degrees, because 150 take away that 90 there. To work out the x, that is the adjacent side in this right angle triangle. It's next to that 60 degrees. So I could say cos 60 equals x over 20. So 20 times cos 60 is going to be 10. So my x is 10. Now to work out my y, that is opposite the 60 degrees. So opposite will involve sine. So sine 60 equals y over 20. 20 times sine 60 is going to be 10 root 3. But I need to remember that it was in the negative direction, it was going down. So actually it will be minus 10 root 3 in my vector. Again, this is much nicer than writing this sentence at the top there. Penultimate example. We're going to do one more example like this, then we're going to do a example going the opposite way. So the wind blows at 10 miles an hour in a northwest direction. I want to write that as a vector, like I've done the last couple of examples. So northwest direction is like that. That's northwest, where this is my north line. If it's northwest, I know that the angle must be 45 degrees. Because remember, northwest is right smack bang in the middle between north and west. But I want to know how much is that going across here and how much is that going up here. I know this angle here will be 45 degrees. And I want to know what's my x and what's my y. I know that this is 10. So the x is the adjacent here. That's adjacent to this 45 degree angle. So I can say that cos 45 equals x over 10 times both sides by 10. So 10 cos 45 is x. So therefore x is 5 root 2. But that's in the negative direction. So I need this to be a minus 5 root 2. And to work out the y, some of you might be able to spot a shortcut of doing this already, considering it's a 45 degree angle. If I were to do it the long way, the y is opposite the 45, so sine 45 equals y over 10, times both sides by 10, so y is 5 root 2. I don't need to worry about it being negative because it's going up, it's going in the north direction, it's positive. And hopefully some of you would have spotted that actually I didn't need to do this calculation here, because if this side here is 5 root 2, then this side here must be 5 root 2 as well, because this is an isosceles triangle. A 45 degree angle is an isosceles triangle. 45 degree right angle triangle is an isosceles triangle. Anyway, last example now for this video. We're going to go the opposite way round. So what about if I wanted to take this vector and write this as a distance and a bearing? So I want to write this as a sentence. How far does this actually travel and in what direction? So let me draw this out. If this is my starting place here, then this vector is saying to go 3 squares in the negative direction, and then it's saying to go 6 squares down, like that. So here is what I've actually done. I've travelled like that. Now, hopefully you can see, to work out how far we've actually travelled from here to here, all I need to do is a little bit of Pythagoras. So if I just do 3 squared plus 6 squared square rooted, I get root 45, or 3 root 5. So that's the distance that has actually been, well, that's the size of this vector. To get its direction, or to get its bearing, well, let me draw my north line in. Remember, this was where I started here. That's my north line. So the bearing that I want will be this angle here, the clockwise angle measured from north. Now, it's a little bit difficult for me to work that out to begin with, but I could work out this angle here. I'll call it A. And then what I could do is, because I know that all of this is 270, I could do 270 take away A, and that will be my bearing. So let's work out angle A. Now, this is the opposite side to my angle A. This 3 is my adjacent, so opposite and adjacent will be tan. So I can say that tan A equals the opposite divided by the adjacent. And if I type that, do tan inverse on my calculator, so tan inverse of 6 over 3, or 2, gives me 63.4 degrees. But like I said, to get the bearing, I need to do 270, take that away. So I'm going to do 270, take away 63.4. And to the nearest degree, that gives me 207 degrees to the nearest degree. So I can say that this vector is the same as travelling, or the same as a size of 3 root 5, if I'm talking about distance, kilometres. Let's just say that for now. I didn't actually specify the units in the question. But that's the size of this vector, and the bearing of this vector is 207 to the nearest degrees. So that's the idea of what a vector is and how we can write them in a nice, easy way, nice, short way, using a little bit of maths and a little bit of trigonometry.